Hi students, in this video, you will learn about percentage U and percentage purity. So prior to this video, you should already know how to calculate the limiting reagent and how to balance equations. Okay, so for this section is found on your lecture notes, page 16. And this is a very simple concept actually. Okay, so if we look at the first paragraph of page 16 on percentage U, you can see that there are many reactions that do not go to completion, alright? And it's actually common especially for organic reactions. And now I want you to highlight this sentence over here. Okay? Whereby the actual U is compared to the U calculated from the masses of the reactants. And the actual U over here is the experimental U that we are talking about. So after going to the lab and doing the experiment, you will obtain an actual U of the products that you get. And the theoretical U is actually the calculated U from the limiting reagent. So you might want to write over here, calculated is from the limiting reagent, okay, that you calculate using the mole ratio. Alright, so now I would like you to actually think of why, is this part, why many reactions do not go to completion. Okay, I want you to think of the reasons, the possible reasons whereby reactions do not go to completion. So this one I will ask you in class. Okay, so please go home and please start thinking while you are going through this session. Alright, and I want you to highlight or box out this box over here, which has already been boxed out for you, because this is the formula to calculate the percentage U, which is the experimental U over the calculated U, the theoretical U, then times 100%. Okay, that will give you the percentage U. So before we go through the example in your lecture notes, I would just like to bring you through one of the analogy, okay, to illustrate this concept. So let's say, for example, you are going to bake a cake, and this recipe that you use will allow you to bake 200 grams of cake. Okay, and the recipe is as follows: 3 eggs, 1 cup of sugar, and 10 grams of butter. So from this recipe, you expect to bake 200 grams of cake. However, after the baking process, when you get the cake, you realize, after weighing it, you realize that you only get 100 grams. Okay? So if you only got 100 grams of the cake, then the percentage U of the cake, in this case, if we use the formula given, the percentage U of the cake will be equals to 100 grams, because 100 grams is actually the experimental U. From experiment, you obtain 100 grams only. So 100 is the experimental U, and theoretical U is the calculated or the expected maximum amount of cake that you should get. Okay, the calculated or expected maximum mass of the cake is 200. So 100 over 200, because it's a percentage, you need to times 100%. Alright, and upon calculation, you should get 50%. So from this recipe, you will realize that you only get a 50% U of the desired cake that you want to get. Alright, so this is the analogy using the recipe. Then now, if we move on to example 12 of your lecture notes, we will see how the use of the same formula can be used to calculate the percentage U of a particular product. Alright, so in example 12, it says that fermentation of glucose, which is this compound given over here, C6H12O6, produces ethanol and carbon dioxide. So part 1 asks you to balance the equation for the reaction above. So even without this part, which is the guiding part in your lecture notes, you should be able to write the balance equation, because the question already gives you the reactant and the products. Alright, so from the reactant and the products, you should be able to form the balance equation. Okay, so in order to balance the equation, I would just like to point out something. Okay, if you look at the reactant, you realize that there are three elements in the reactant: carbon, hydrogen, and oxygen. When you want to balance, you should first look at the atom that is only present in one of the products, because now you got two products. So if you look at carbon, you realize that both of these products, they contain carbon. If you balance hydrogen first, then you realize that only this product contains hydrogen. Okay, only this contains hydrogen, the carbon dioxide doesn't. But if you balance oxygen first, you realize that both products got oxygen as well. Okay, so therefore you know that the first element that you should balance should be hydrogen and not carbon or oxygen, or else it will be difficult for you to balance both sides. Okay, so if we now balance hydrogen first, over here got 12 hydrogens, and in ethanol there are 6 hydrogens, therefore you know that over here there should be a 2. Okay, then after that you balance carbon or oxygen, up to you. Okay, if I balance carbon first, I realize that there are already 4 carbons, because 2 times 2, 4 carbons. So over here I need another 2 more carbons. Then I see whether my oxygen is balanced or not. So in this, my oxygen, I got a total of 2 oxygens. In this, I got a total of 4 oxygen, because 2 times 2 again. Alright, so altogether in my products I got 6 oxygens. And in my reactant I also got 6 oxygen. Okay, oxygen atoms. Therefore, I know that this equation is already balanced, so this one should be a 1. But whenever you write a balance equation, if it is a 1, you do not need to write anything. Okay, so you can just cancel this line away. Alright, so the balance equation should be like this. And then if you look at part 2, it asks you to calculate the mass of ethanol, which could be formed from fermentation of 100 grams of glucose. So glucose is the reactant and ethanol is the product. Wherever you see mass, the number one thing that you need to do straight away is to calculate the amount. That will earn you 1 mark. Alright, so 100 grams, and then you will calculate the amount of glucose. Okay, so if you calculate the amount of glucose, you should be able to get this. And then after that, if you use mole ratio, you will realize that the amount of glucose over amount of ethanol is 1:2. 1:2. Therefore, it's 1/2. Okay, by mole ratio. Hence, the amount of ethanol is this amount. Okay, then after that, in order to find the mass of ethanol formed, you need to use number of moles equals to mass over mR formula, and you'll realize that the answer is 51.1 grams. This one you should be able to do it easily, because this is O-level chemistry. Alright, and the next part, which is to calculate the percentage U if only 6 grams of ethanol was formed. Okay, so this one you need to use the formula. So from what you have calculated, the 51.1 grams, that one is actually, if you ask yourself, can you ask yourself this question, is it experimental U or theoretical U? Okay, the 51.1 gram. That one is calculated using the mass of the glucose that you use. So from the mass of glucose that is reacted, 51.1 gram of ethanol is expected to be formed. So that is the maximum amount of ethanol that can be formed, alright, from that 100 grams of glucose that you use to react. However, now the question tells you that only 6 grams of ethanol was formed. So this 51.1 gram is actually the theoretical U, whereas the 6 grams, this one is the experimental U. Okay, so percentage U will now be equals to 6.0 over 51.1. And because it's percentage, therefore you multiply by 100%. And you should be able to get 11.7%. Alright? So that is simple enough. Okay, now moving on to percentage purity. Okay, so please take some time to go through percentage yield again before you move on to this part, which is percentage purity. So if we use back the same analogy, the one on the cake. Okay, if let's say now, out of the 100 grams that you weigh for your cake, actually there is whipped cream on the cake. Okay, actually there is whipped cream on the cake, which means that this 100 grams is not purely the weight of the mass of the cake. Okay, because there is other substances that is not cake make up of the recipe, which is the 3 eggs, 1 cup of sugar, and 10 grams of butter. Alright, and therefore the percentage purity of the cake is not 100%. Alright, so there is an analogy here. Now, if we look at reactions, can you highlight this part? So in reactions, due to contamination or reaction with the air, sometimes reactions may not be pure, which means the product obtained may not be pure as well. There could be impurities. Okay, so I give you an example. If a metal, let's say for example, iron. Okay, if you want to obtain iron, pure iron, although your expected percentage purity of the iron is 100%, but because iron, when it reacts with air, it could possibly form iron oxide, which is your rust. Okay, and therefore the purity of iron inside your compound may not be 100%, because out of the mass obtained of your iron, some of it could be iron oxide. It may not be purely iron only. Okay, and therefore it may not be pure. So can you now also think of some other real life examples whereby percentage purity is actually an important concept? Okay, so this is your homework. Okay, think of real life examples whereby percentage purity is an important concept. Okay, so for percentage purity, the formula is actually this one. Is equals to the mass of pure substance over the mass of impure sample of the substance times 100%. Alright, so if we use back the cake example, let's say out of the 100 grams that you weigh, 80 grams is actually pure cake, and 20 grams is the whipped cream. Then it is 80 over 100 gram times 100%. So the percentage purity should be equals to 80%. Okay, I repeat. So if we use back the cake example, after weighing the cake, you realize that it's 100 grams, but this 100 gram is not only the pure cake that you want to weigh, but also the whipped cream on the cake that you put after the cake is being baked. Then the mass of the pure cake is 80 grams because the whipped cream is 20 grams. And then after that, because you need to divide it over the mass of the impure sample of substance, which is the total mass plus the mass of the cake plus the whipped cream, which is 100 grams. So you take 80 over 100 times 100%. Alright? So if we take a look at the example given in your lecture notes, page 17, we'll go through this concept together again. Alright? So chalk is almost pure calcium carbonate. So by now you should know what is calcium carbonate. Calcium you know is Ca2+, and carbonate ion is CO3 2-. So calcium carbonate is actually CaCO3. And the question tells you that 10 grams of the chalk was reacted with an excess of dilute hydrochloric acid. The question already tells you which one is the limiting reagent and which one is in excess. Then the volume of carbon dioxide gas collected at standard temperature and pressure was 2.13 dm cube. So underline this information as well, and make sure you underline standard temperature and pressure. Immediately under standard temperature and pressure, put down 22.4 dm cube. Alright, so in part 1, the question asks you to write a balance equation for the reaction between calcium carbonate and hydrochloric acid. This one should be no problem at all. So if you write the equation, this is actually acid plus carbonate reaction in your secondary school syllabus. So you will form calcium chloride, CO2, and because there are 2 hydrogens over here, so you need 2 over here as well, and you realize that the equation is already balanced. Okay, then part 2, calculate the amount of pure calcium carbonate present. So for pure calcium carbonate, it must be the amount that has reacted with the dilute hydrochloric acid. Alright, because in the question it says that chalk is almost pure, so it is not pure. It contains other species as well, okay, other impurities. So in order to find the pure calcium carbonate that is present, you need to use this information, the volume of the carbon dioxide gas collected, because carbon dioxide gas is only collected, okay, is only collected when your calcium carbonate reacts with your hydrochloric acid over here. And therefore, using the volume of CO2 collected, you will be able to work backwards to find the amount of calcium carbonate present, okay, the pure calcium carbonate present. Okay, so this one is very simple. You know that the volume collected is 2.13, so the amount of calcium carbonate, pure calcium carbonate, present is equals to 2.13 divided by 22.4, and you should be able to get 0.0951 mole. Alright, and in part 3, it asks you to calculate the percentage purity of calcium carbonate in the sample of chalk. So in this question it says hence, which means that you need to use part 2's answer. But even if the question didn't say hence, because it is part 3, part 1, part 2, part 3, you must know that they are linked. Okay, which means that you must know that you need to use the information from part 2, the answer you obtain from part 2. So you obtain 0.0951 moles of pure calcium carbonate in part 2. And from there, you can actually calculate the mass of pure calcium carbonate, correct? Which is equals to 0.0951 times the MR of calcium carbonate. If you calculate, you will realize that it's 100.1. Okay, if you cannot calculate this MR of calcium carbonate, come and see me. So from here, you should be able to get 9.5195. Okay, usually for the answers that I get in between the steps, I will leave it to 4 sig feet. But over here, if I leave it to 4 sig feet, I will realize I will actually get 9.52. Okay, 9.52, because I will use 5 to round out my 9, and I will get 9.52. So I will just leave it as 9.5195 first. Alright, and in order to find the percentage purity, I know that the mass of impure sample of substance is 10 grams because the impure substance is the chalk. So it's 10 grams, the chalk is 10 grams. So my percentage purity is equals to 9.5195 over 10 times 100%. And you should be able to get 95.2%. So for all calculated answers, make sure you leave it as 3 sig fig unless the question tells you otherwise. Alright, so I repeat, for the steps in between, leave it to 4 sig fig, but for your final calculated answer, always leave it to 3 sig fig unless the question tells you otherwise, which means unless the question specifically tells you to leave it in a certain number of decimal places or a certain number of significant figures. Alright, so this is the end of the section on percentage U and percentage parity. If there's any question, you can come and look for your own teachers. If not, we'll need you to revise both example 12 and example 13 and do tutorial question B11. The next lesson, there will be a quiz on percentage U and percentage parity, and it will be very similar to either of these 3 questions. Example 12, example 13, or your tutorial B11. Okay, so that's all.